So, Assalamu alaikum, guys. So, in last part, we have seen in this chapter number 6 that counters are of two types, uh, ripple counters, and another is the asynchronous, any ripple counters or asynchronous counters, and another one is synchronous counters. So, we have seen the examples how to design these ripple counters, and the design is actually the fixed design which we have seen in the previous lecture. So let's now move and just conclude what we have learned in asynchronous counters. So here in asynchronous counters, basically uh, we have seen that there is a propagation delay. Because of the output of one flip-flop is connected to the input for the next flip-flop, and so on. So we can have, depending upon the counter itself, we can have multiple, stage of or multiple flip-flops. So if we have more flip-flops, the delay will be more, basically because of the propagation. So these type of flip-flops are actually prone to this propagation delay problem, because of all flip-flops are not updating status simultaneously. All right, so you can read some points here. Flip-flops cannot be triggered simultaneously, producing an asynchronous operation. That's why we call these asynchronous counters. Next, here in this type of counters, we can see this is a down counter, and previously we have discussed the up counter. So in down counter and up counter, there is a very minor change which even you can observe here, and that change is the clock itself. So for the up counter, we used this negative age clock triggering, but here if you observe, it is a positive age triggering here. So this is the only change in up and down counter. So if we use the negative age triggering, it's become up counter. If we use the positive age triggering, which is in this case, which you can see here, it becomes a up count, a down counter, basically. Okay, so this is where otherwise everything is very much similar. We need to set up both the inputs of JK flip-flop to the high so that it can work in a toggling mode. Same previously we have seen, then everything is going to be same. Okay, so this is the explanation of the down counter. So as we use here the positive age triggering, so we can highlight the positive ages of the clock, which you can see here, and the reference line is already drawn here, right? So initial values, we are considering that all flip-flops are at 000. So we know that this clock is triggering this QA, basically the first flip-flop. So, and this one will be triggering the next one. So this is the positive age of this flip-flop, left flip-flop output. All right, so based on that, the next one will be triggering. So we can see that now as this is triggering, so 0 will become 1, 1 will become 0, this is 1, this is 0, this is 1, this is 0, because of this is the leftmost flip-flop, which is triggering every any positive age. And now this any waveform going to trigger the next stage of the flip-flop. So again, it is a positive age. So we can highlight the positive ages. This one, you can see the frequency is now half of that one. So we can observe here 0 as this trigger comes. So it will become 1, and it will be 1 until the next age comes. So next age is here. So this will become 0, 0 until the next age comes. This will be 1, 1. This will be 0, 0, like that. Now, this waveform, yani QB, is going to serve the clock or will be going to trigger the next stage. So again, so we can see as this age come, what happened? This triggering, yani toggling will operation will perform. So 0 will become 1, and it will be 1 until next age of the positive age comes. So we can see now this is the positive age. So this one will become again 0. Okay, it will be until the next. So this is the counting. Now you can read from up to down, down to up. So this is the 111, yani it is a 7 count. Then this is the 6 count. This is a 5 count, 4 count, 3, 2, 1, 0, and then again, start repeating. So this is the operation of the down counter, which you can see from here as well. All right. So working of the down counter, 3-bit down counter. All right. So an up counter using n flip-flops count upward from a minimum count from 0 to 2's power n minus 1. We can see here. And a down counter using n flip-flops counts downward from, so a maximum count will be 2's power n minus 1 to 0. So n is basically number of bits, right? We know this one. It is the number of. So what is n here? N is the number of bits. So we know that if we have n is equal to 3, in the like the previous case we have seen, n is equal to 3. So it means 2's power n minus 1 will be 2's power 3 minus 1, which is 8 minus 1, which is 7. So it will count from 7 to 0 basically. Okay. This is the basically the order how the counter will be counting from highest value to the lowest value in case of down counters. Next thing in asynchronous decade counter comes the decade counters we are going to discuss now. So decade counters means basically the counter with state less than this number are possible also. Like in previous case, we have seen that if n is equal to 3, so number of states maximum will be 8. All right, n is 0 to 7 or 7 to 0, whatever in case of up and down counter. But we can also have some counters which has less states which then the maximum they can have, like 8 is there. So we can have some counter they can have 5 states, 4 states, and there are some states which is basically truncated. Okay, what we call, so they are designed to have a number of states in their sequence which are called the truncated sequences basically. Okay, so these sequences are achieved by forcing the counter to recycle before going through all the normal states. Okay, so instead of we need to forcefully reset the counter before reaching to its last count or the maximum count or minimum count, whatever. We need to make it recycle before that or reset before that. So common modulus of the counter with truncated sequence is the mod 10 or 10 state counter, and you know that 10 states will be means 0 to 9, and 0 to 9 is basically BCD counter. We are talking about the BCD counter. So if you want to design the BCD counter, at least you need four flip-flops. Means 4, like 0 0 0 0 will be the first count, and it will keep on increasing and it will reach to maximum 1 0 0 1, which is like 9. After that, we know that if it is a normal counter, if not a decade counter, it will also go after this 9, it will go to 1 0 1 0, yani, which is 10, then 11, then 12, then 13, 14, and after 15 it will go to 0. We know this one. But in order to have a BCD counter, what we have to have, that it must go from 0 to 9, and as it try to reach to 1 0 1 0 count, which is the 10th count, we will be forcing this counter to be reset, yani go to 0 state. This is what we have to do in case of decade counter. So let's see this thing in more detail. Okay, before this one, we can just discuss this decade counter, which I just, then I will go back to the case 21. So this is BCD ripple counter, which you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And after 9, it is going to the 1 0 0 0, like that. So we know that after 9, the normal counter will go to this state, which is 1 0 1 0. But what we are going to do, as our counter try to go to this 10th count state, will be forcefully resetting our counter. So see the design. So again, it is a ripple counter design. It is a fix. So we can see we have a 4 flip-flops here. 1, 2, 3, 4. All right, and all are set to high because of need to be set in toggling mode. Then what we are having, you remember that the control, which is the clear control, every counter have two control, reset and preset. So we have a clear control and we have a set control. So we are going to use here clear control, and we know that if this signal is 0 because of it is active 0 by the bubble, it means the this flip flop will be clear. So we are connecting a common line to this clear control, and this is going to be controlled by this gate. And what is the input for this gate? The output of Q1 and the output of Q1 and the output of Q3. See, so how it counts, basically we know that the rightmost is the most significant bit always, means this bit is Q3, then we have a Q2, we have a Q1, then we have a Q0. So here you can observe that whenever this Q2 and Q1 both are 1 1, right, at same time, which you can see that in this count, in these states, they are not 1 1 at the same time. They are only 1 1 at the state of 10 count, which is 1 0 1 0. So we are developing a logic that if this signal is 1, if this signal is 1, there will be 1 when we reach to this count. Before that, one of the input will always be 0. You can see in this state diagram, right? So whenever both are 1 1, the NAND gate actually produce 0 at that time. When it produces a 0, so it will quickly reset all the flip-flops, and it will go from 9 to directly 1 0 0 0, yani initial state. This is how we are forcefully resetting the counter before moving to the state 1 0 1 0. So this type of counters are called the decade counters because it has 10 states. All right. We can also ask you, what is the mod of this counter? Mod means the number of state a counter will pass through. So we can see here we have a 10 states. So mod of this counter, BCD counter, is mod 10 because we have 10 state. But see, if it is not a decade counter, normal binary counter, so definitely it will go through all 16 states, yani 0 to 15 it will go. But we are designing here a BCD ripple counter, so we don't need there are unused state after 9, 10, 11, 12, 13, 14, 15. So we are truncating these sequences to design. All right. So this logic can be developed in a variety of ways. It's not like we can only use Q2 and Q1. If we want to use Q3, Q0, we can also use it. So I'll show you a few other design for this one. Let's go to the previous slide. Here we are discussing the mod 6 counter, up counter. Mod 6 means there will be 6 states. Okay. And this is an up counter. It means it will go to 0, 1, 2, 3, 4, 5. Means 0 to 5 states will be there. After 5, it must go to 0. So what are the sequences which are skipped now? So it means 6, 7. These two sequences are not there. Okay. Because maximum count is 5. So at least we need here 3 flip-flops. So we are using here 3 flip-flops. Flip-flop 1, 2, 3. All are same thing. It is an up counter. So we are going to use this negative age triggering method, and all flip-flop are set to inputs J and K set to high so that it can work in a toggling mode, and then so on. So here we are going to reset this one again. So it is a mod 6, 0 to 5 it will go. So when it means is that mod 6 says like 1 1 0. This count we don't want. So here this is any high any QC, this is QB, this is QA. So we whenever this count is like that, QA is 0, QB is 1, QC is 1, we are going to forcefully reset all the counters. So we are using here QA, this is QA, it must be 0. So that's why you can see this is the red line. And then we are using here a NOT gate. So whenever this is 0, we will be having here 1. Rest QB and QC both are 1 1, we can see. So it is 1, it is 1. Okay, so now all three inputs of this AND gate is 1 1. Then only we can have the output 1. So we can see this time it is an active high type clear control. It is not the bubble here. You have seen the previous case there was a bubble. So that will be reset when the value of that input is 0. But this time it is an active high type. So it means whenever this is 1, it is going to be clear. So it will go like this: 0, 1, 2, 3, 4, 5, 6. As this count reach, it will from this quickly go back to this state and so on. So this is the decade counter. Same way you can have mod 6, mod 5, mod 4. So mod 7 even you can design. Okay, different type. So this is the logic basically that can be. Again, in this here also, if someone want to use only two inputs like QC and QB, because both are 1 1 at the same time, so we need to check it. Are they they are same, like 1 1 before this sixth count? So like this is the sixth count. If we go back, we can see they are not same. This is 0. They are not same. This is again 0. This is 0. This is, so at least one input is 0 before the sixth count. So again, if you want to use this logic, QC and QB, we can also use it. Okay, so how can we use this one? Let's see this one. Just erase everything here. So if we erase, erase all, no. So if you want that logic that whenever these are QC and QB is 1 1, so we can skip this. This was not needed. So in this case, this line, no need. We can delete this one. So this one simply work this AND gate with two inputs. One input is QB, another input is QC, like this one, right? This one. So we are having logic here that whenever both are 1 1, they are 1 1 only at the count of 6, and that which is we want to reset at that time. So this is 1, this is 1, so logic will be 1. And before that, you can see one input is always 0. So if before the count yani 0 to 5, one input will always be 0. Because of this, the output of this will be always 0. So flip-flops will not reset. It's like that. So this is the way how can we forcefully reset the counters in order to design the T-gate counters. Hope it is clear to all of you, right? Now, this is ripple counter. Now it is ripple counter already. I explained how it works. So like it works from 0 to 9, and from 9 it goes back to 0. This is another design of the ripple counter, which is in the book. But you can see this one. This is the easiest design. Okay, so you can focus on this one because this implementation is easy. But as you know that I always said, like, this is not the only any. There is always a different way of designing possibility. Like here you can see in this book. So we have one more kind of design for the BCD counter, which you can see here. So just to show you that there is not only one solution of a problem, we can have multiple solutions. This is one of them. But for now, I think the one which I show you, that is the more easiest one compared to that one. But just for your comparison, you can also see this one. It is in the book, and detail you can find in the book. This is BCD ripple counter, because of a single BCD counter can count from 0 to 9. What if you want to count further? For example, 0 to 99. So we can connect these counter in cascade fashion. So this can count from 0 to 9. All these together can count 0 0 to 99. These three can count 0 0 0 to 999. Yani three can we count 1000 counts, 1000 states basically. Okay, that is also possible. So altogether we can go from 0 to 99 count. So problem with asynchronous counters, we have seen that there is an issue with the delay issue, which we call. So because of if we have a long chain of the flip-flops connected together, so there will be a delay, more delay. That is the issue with the asynchronous. So problem occur if this delay is longer than the response time of other logic element. connected to the circuit. So how can we eliminate this problem of propagation delay? The solution is the synchronous counters. So synchronous counters overcome the problem of the propagation delay and erroneous intermediate state. This is in this type of counter, all flip-flop clock inputs are wired together, so the transactions of the all states occur simultaneously. So we'll discuss now synchronous counter design. Okay, next. So in synchronous counter, we are going to use a common clock for the all flip-flops, not like the, here in case only one flip-flop and next one is the output. Clock will be the output of the previous stage. So design of synchronous counters, guys, is actually very much similar to the chapter number 5, design of synchronous circuits. Exactly same, okay, with minor change, which you will see here now. What is the change? I will explain, inshallah. So again, first of all, you need to decide the number of flip-flops you need to design. Then you need excitation table. Then you will be having a state diagram. From that state diagram, you need to use use the K-map and find the equation. And then finally, you will be drawing the circuit for the counter. So let's see this one. The question is like design a 2-bit synchronous counter using, for example, JK flip-flop. So when we say 2-bit synchronous counters, it means we are going to have 2^2 4 states. All right, and it is an up counter, so it will go from 0 to 3. It means, all right. So we can say the 4 states, like say A, B, C, D. So in binary, we can write A means 0, 0, 0, 1, 1, 0, and 1, 1. We can say like this. Okay. So here, this way, we can just tell what is this state, each state in binary like this. Okay. So we can just have this state diagram, A to B, B to C, C to D, and can write their binary values here, right? And then after, we also need to use the excitation table in case of design of synchronous counter. We have seen synchronous circuits, we have seen. So we have this one for the JK flip-flop, right? We will be using this one. So next step is after 1, 2, 3, we need to develop the table. So in this table, because the present state we can mention, always write in an order, 0 to 1, 2, 3. Then we have a next state, and then we have a flip-flop equation. So we can also call this one excitation table, because in the excitation table, what we have PS, present state, we have NS, next state, and what we have, flip-flops inputs. These are the flip-flop inputs. So now, we have seen in the previous slide that we have first state 0, 0, next state is 0, 1, then 1, 0, then 1, 1, and these are the arrow is telling you how the states are changing. So when you have 0, 0 state, next state will be 0, 1, present state is 0, 1, next state will be this. If present state is 1, 0, next state will be 1, 1, present state is 1, 1, next state will be 0, 0. Now based on that, what we have to do now, we'll be using this excitation table and completing the flip-flop equation. So need to focus where the present state of A, next state of A, 0, 0. So from this excitation table, we can see it should be 0, don't care. Next one, 0, 1. So 1, don't care. Next one, 1, 1. It means don't care, 0. 1, 0, which is don't care, 1. Now we can focus on B present value, B next value, which is 0, 1. So 1, don't care. Same, 1, 0, which is don't care, 1. Then we have 0, 1. 0, 1 means 1, don't care. Then we have 1, 0. 1, 0 means don't care, 1. All right. So once you completed that one, you need to use the K-map, and then you need to find the equations for the all JA, KA, JB, KB. Okay. So we need to use the 4 here K-maps. See, the change between this table and the table which we form in chapter number 5 is that there we have external input and output, but in case of counters, We don't have any external input, external output like X and Y was there. Here you will be having present, next, and flip-flop equation. So this is any more simple compared to that one. So now what we have to have, we need to have the K maps, 4K maps. So quickly I am showing you. This is A and B. This is 0, 1, 0, 1. And then for the JA, you can see you have only one minterm, which is at 0, 1. So this is like here. Other than this, you have two don't cares, which is 2 and another one. So these are two don't cares, right? So when you form this one, so you can see that this is the group of one. Okay, this one. Okay, so what you will be getting, this one output will be simply this is for JA, so you are getting for the JA B. Okay, this is for the JA. Similarly, you can go for the next one. So two don't cares, which is here, and then we have last one only here, this one. So you can make it this one again. So you will be getting Ka is equal to B. All right, same, you can go for one more K map. This is for the JB, and this is one don't care, one don't care. So this time, because of the K map is completely filled, so the groove will be like that, guys. Okay, and then we can, so this means is that what we are getting JB is equal to 1. You know that one, when the complete is filled. And then same, we can go for the last K map for the KB, and don't care 1, don't care 1. You know that again, completely filled K map. So it is a group of 4 again, and then you have, so you will be having KB is equal to 1. You know, so now what you got? You got JA equal to B, KA is equal to B, means the flip-flop A, both inputs are B. For the B in flip-flop, we have both inputs 1. That's all. Now you can design simply. Okay, so I'm going to erase everything here, and I'll show you how can we design this one. Okay, let me see. Okay, so I will delete it here, and I will show you the final design of this counter. So just erase everything, and then see the design. So for the design, you just writing what we got earlier. We got JA is equal to KA is equal to B, we got, and then JB is equal to KB is equal to 1, we got. All right, so do the design. So two flip-flops of this counter we have to have. Another one will be having like this. So outputs, similarly two inputs. This is JA, KA, JB, KB. All right, these two inputs are gonna be connect to B. You can see this one B, and this is output B, guys. This is output A. So this will be connected to here. These two must be connected to logic 1 or logic high, whatever we can say, we can connect. Other than this, the most important thing is the clock, which you should not forget. Clock here. Up here, guys, you can use any clock, no problem, whether negative age or positive age, because of this is a synchronous circuit. Okay, and the clock is going to be the common. That's all. So connect the same we use here, positive age triggered, and connect both of them, and that's fine. So this is your 2-bit up synchronous counter that will count from 0, 0 to maximum 1, 1 in a loop. So this is the design, So this is similar to what we have discussed already. So it is a 2-bit. Okay. For example, you want to design a down counter. Okay. This is an up counter, which I show you. Down counter. So like the previous ripple counter, we have seen, just change the positive age to negative age, and negative to positive, we can change it. But here you don't need to worry about the clock. You can use positive age or negative age for both type of counters. But how can we design the down counter? Now you will see here. So the main role is here, how you are writing the next state. So I have already explained to you the up counter. For the down counter, guys, the your table, sorry, this state diagram will decide how your counter is working. Like for the down counter, will be going from this way, this way, this way, and this way. This is the change. So based on that, you have to write the next state, guys. So if our present state is 0 0, and from this state diagram, which is counting down, all right, it should be 1 1. Present state is 0 1. You can see from here what is the next state in the state diagram. 0 0. This is 1 0. What is the next state? 0 1. Present state is 1 1. What is the next state? 1 0. So change will be happening here in the next state for the up and down counter. So we need to follow this state diagram. If it is counting down, so we will be designing the down counter because we are writing the next state according to the state diagram. All right, so this is the change. Now when we go to this one, and we'll be designing this one, so our counter will be basically that down counter automatically. We don't need to do anything. Later on you can use positive age triggered or negative age triggered clock, whatever you want to use, you can simply use. So this is about the synchronous counter design. It is a 2-bit. Same, you can go for 3-bit, you can go for 4-bit. So what you have to know, you must know the excitation table. If you want to use SR flip-flop, you can do it. T, you can do it. JK, you can do it. You can use any flip-flop. It doesn't matter. Getting the point? You can use anyone. But excitation, you have to, table you must remember or memorize. This is the example of 4-bit synchronous. See, 4-bit is actually going to be very lengthy. So at least you should have a practice of 2-bit and 3-bit synchronous counters, because for the 4-bit, 2's power 4 yani 16 combinations. So it's going to be very lengthy, 16 combinations, 16 present state, 16 next state. But yeah, but you must know how it is designed. So we have a design for your reference. Next thing is, after ripple counter, synchronous counter, we have some special purpose counters called the other counters. So counter with unused states, yani a counter which have some unused states, okay, in their count. We can see this one. And other than this, so just a minute. Okay, so the counters with unused states will be looking in detail now. So one by one we'll see. So design a counter with unused state. Guys, if you look this state diagram, you can understand it is a 3-bit counter which we can see in each state. So state 0, then next state is 1, next state is 2, next state is 4. So which one is skip? 3 is not there. Then from 4 we have a 5, then we have a 6, then we are going to directly 0, and 7 is also skip. So 2 states are here skip. So what we call this one unused state. Some states are missed in the maximum possible state. So this is basically unused. So the design, again, very simple, same what we have explained. So first of all, you need to write the present states. So you will be always writing in an ascending order, minimum to maximum value, 0 to 7, just write it. And next state, you will be following the state diagram, which is here. So present state is 0 0 0. What is the state in state diagram? You will be writing here. If present state is 0 0 1, next state is 0 1 0. Present state is 0 1 0 in the state diagram. Next state is 4, guys. You can see here, this is 4. So you should write 4. Now next 0 0 1. Now this state, present state, is not available in your state diagram. We can see this is the missed. So for that, you can simply fill don't cares in this. In complete row, you can fill with the don't care. Here actually, this is going to be twice because of JAKA. Same for this one, twice. Same for this one, twice. Okay, we are just writing one time. It is actually twice for both inputs. It should be like that. Okay, so now just complete this way. Now you have 4. Next is 5. You have 5. Next is 6. You have 6. Next is 0, not the 7, which because of we can see it's now for the 7. Just write all the don't cares. That's all. Other than this, everything is gonna be same. These are going to be the don't cares. This is don't care, right? Okay, a flip flop input you need So for that, you will be using this excitation table. So use check present state of A, next state of A, then write the flip-flop equations. Same present state of B, next state of B, then write this one. Present state of C, next state of C, just write this one. This way you can complete this table, and then you have to use the K-map. So there will be some min terms and there will be some don't cares here. So you need to solve the K-map with the don't care conditions and get the equations for all flip-flops inputs, right? 6 K-maps you have to use, and then finally you will be designing your circuit. So this is the design. You can see the common clock, okay, positive we are using here, connected everywhere. JK value is connected, means is both are coming B. You can cross check your answers, and then and so on like that. So first you just complete this one and design this one, and you can match your answer here. So this is unused states. Okay, so special counters we call this type. Next is the ring counter. So in the ring counter, guys, it is again a special purpose counter. Just look here the state diagram of this ring counter. So here we have a reset button. So whenever we press the reset button, so our counter is not going to set all 000. Instead, it is going to set in a way the leftmost will be the 1. Rest 3 flip-flops are going to be 000. Yani they are going to be reset. But the first one is going to be preset. You know the preset. Yani we can set the value to the flip-flop 1. Reset means set the value to the flip-flop 0. So next count is like this one. So you can see the 1 is actually shifting right side here and rotating. Yani this 0 is rotating here and shifting right. Same, rotating here and shifting right. Rotating 0 here, which you will be getting here and shifting right. And from here, rotate again here and shifting right. So 2 operations are happening here. Shift right and rotate, okay, which you can understand from this figure. So we have a shift register basically, and shift register design we have seen in the beginning. It is basically made up of D flip-flop, data flip-flop. So output of this one connected here and here and here, shifting right 1 bit, and then this is going to be the rotate here, the loop. So this is basically the design. Okay, since the ring counter example shown above has the 4 distinct state, so the mod will be the mod 4 of this one, right? So this is shown with the help of clock. So common clock we are going to use here. And then we can see QA initially 1 and QB, and this one is going to be the 0, 0, 0, and this is the 1, yani this first count. So as the clock comes, we can see this 1 will be shifting to the QB. So count will be 0, 1, 0, 0. Next count will be 0, 0, 1, 0. Next count will be 0, 0, 0, 1. So 1 reached to the last now. So this will rotate now again. So same way. So 1, 0, 0, 0. So 2 operation happening in the ring counter, shift right and rotate. So now point is that how can we manage this if someone reset the counter? So leftmost must be the 1, rest must be the 0, 0. So look the design now. So first of all, we are going to use the shift register. So it's very simple. We have register 1, any flip-flop 1, 2, 3, and 4. And the output of this one is the input for this one, output of this, input of this, output of the input is it. And then we have a Q3, Q2, Q1, Q0. So guys, this is the shift register, and then rotation happening like the output of this one connected back to the previous state. Common clock is connected because of it is a synchronous counter. Reset control is here, connected to here, this, but this one is not going to be reset to 0. Instead, it is going to be the preset. So this is going to be connected to the preset control. So whenever we press the reset control, even if there is a clock or not, okay, whenever we press the reset, so Q3 is set to 1 because of it is connected here, you can see, and Q2 will be 0, 0, 0 because it is connected to the reset control. Now, after that, we remove the reset. Then we are just looking for the clock. So first clock, what happened? This 0 is going to be the, 1 is going to be shift to the next state. And then this 0 is going to be the rotate here. And this is going to be shift here. Now, next count, this will shift here and this will rotate here. Again, this will shift here and this will rotate here. And when it is reached to here, so this will rotate and reach here. So shift and rotate operation is happening in the ring counter. So this is a special purpose counter, okay, special type counter. Last one is the Johnson counter. You can see the state diagram of the Johnson counter. So when someone reset it, all flip-flops going to be 000. Yani we are going to connect the reset button control here so that everyone will be 00. But see the next count. In the next count, what happening? The one insert here. Yani what happening? With next count, 2 1 is entering here. Then the third count, 3 ones are entering here. Yani shifting operation is there, shifting right, but inserting ones. And see, fourth count, what happened? All ones are here. But after when all inputs become 1 1 1, yani all state become 1 1 1, what happened? This time zero start entering. So basically, here also shift right and rotate operation are happening, but the rotation which we are rotating here, not rotating the exact value, instead we are rotating the complement value. Yani this 0 will be here, 1 in the next count, which you can see again when we rotate this one. So this is 0, its value and complement will be 1. Now again 0, so its complement will be 1. Again 0, its complement will be 1. So now when all are zeros, 1 1 1 1, next time again, because the last yani rightmost is the 1, so its complement will be 0. So it's rotate now again. As it rotate, so it rotate the 0 value. Now the last bit is 1, so this one will rotate and it will be 0 again because of the complement value. Then shift right again and it will rotate again, and the 1 will be rotating as a 0. And then the still it is the 1, so it will rotate its complement value, rotate and complement value will be inserted, so it is gonna be like this one. So the design, just minor change in terms of ring counter and Johnson counter, you can see here. And what is that? First of all, it is also performing shift and rotate operation. So we have 1 2 3 4 count flip-flops. But guys, instead of rotating the regular value, we have seen we are not rotating the regular value, but we need to rotate the complemented value. You know that each flip-flop had two output, one is regular, another one is complement. So this is the complemented value. So when the count is 0 0 0 0, yani the rightmost value is 0, so the complement value will be 1. Are you getting the point? So what happened, as the clock come, this one will rotate. So because of this, if this is 0, so with the clock, what happened when we, for example, clear. So clear control is here, yani connected to all flip flops. So all will be 0 0 0. Okay. Now when we remove the clear control and look for the clock, so first clock. So because of this is 1, so this is gonna be rotate and we are going to have this one here. Still QD, which is still 0. So complemented value will be 1, rotating 1. It is still 0. The complemented value here will be 1, rotating like this. Complemented value will be 0, rotating. So now this time it's become 1. So when it is become 1, the complemented value will be 0. So 0 start rotating. Still 1, 0 start rotating. Still 1, 0 start rotating. Still 1, 0 start rotating. Now it's become 0. So what happened? It go back again in the beginning. So this is how a Johnson counters basically work. So if the question come regarding this, what is a Johnson counter and how it works, or look the design. So this is the design. You must know how it is designed. So basics you must know. So as we can see, there are 1 2 3 4 5 6 7 8 states are there. So it is again mod 8 counter. So this is the Johnson counter, guys. Okay. So I think this is the last one counter in this chapter. So this way we had done with this chapter. Some homework questions, a practice question from which you can find at the end of the book. Okay. So hope you understand this chapter thoroughly, completely, and we'll be meeting in next lecture. And we start the new chapter, chapter number 7, inshallah. Okay. So you can practice these homework questions which you can find at the end of the chapter. All right. Thank you.